Today we're diving into one of the most important frameworks in modern physics, the Standard Model of particle physics. This model is like a blueprint for understanding the fundamental building blocks of the universe. It describes the basic particles that make up everything around us and the forces that govern their interactions. Whether you're curious about what makes up matter or how forces like electromagnetism work, the Standard Model is at the heart of it all. Let's start our journey by exploring what this model is and why it's so essential to science. Standard Model didn't appear overnight. It's the result of decades of research and discoveries by scientists all over the world. In the early 20th century, physicists began to uncover the existence of subatomic particles like electrons and protons. As experiments became more advanced, new particles were discovered and theories were developed to explain their behavior. By the 1970s, these ideas were unified into what we now call the Standard Model. This model has since become a cornerstone of physics, helping us make sense of the universe at its most fundamental level. The heart of the Standard Model are the fundamental particles. These are the smallest known building blocks of matter. The model organizes them in two main groups, fermions and bosons. Fermions include quarks and leptons, which make up matter, while bosons are force carriers. Understanding these particles is key to understanding everything from atoms to galaxies. As we move forward, we'll take a closer look at each type and see how they fit into the bigger picture of the universe. Quarks are one of the two types of fundamental fermions in the Standard Model. They come in 6 flavors: up, down, charm, strange, top, and bottom. Quarks combine in various ways to form protons and neutrons, which are the components of atomic nuclei. What's fascinating is that quarks are never found alone in nature. They're always bound together by the strong force. This unique property makes them essential to the structure of matter as we know it. Leptons are the other type of fundamental fermions. The most familiar lepton is the electron, which orbits the nucleus of an atom. But there are 6 leptons in total: electron, muon, tau, and their corresponding neutrinos. Leptons don't experience the strong force, which makes them quite different from quarks. Neutrinos in particular are incredibly light and rarely interact with other matter, making them some of the most mysterious particles in the universe. Bosons are the particles responsible for carrying the fundamental forces in the Standard Model. Each force has its own boson: the photon for electromagnetism, the W and Z bosons for the weak force, and the gluon for the strong force. There's also the Higgs boson, which gives particles mass. Without bosons, the universe would be a very different place, as they mediate the interactions that hold everything together. Standard Model describes 3 of the 4 fundamental forces in nature: electromagnetism, the strong force, and the weak force. Gravity, although crucial, is not included in the Standard Model. Each force operates over different distances and strengths, shaping the universe in unique ways. Understanding these forces helps explain everything from why atoms stick together to how the sun shines. Electromagnetism is the force responsible for electricity, magnetism, and light. It's carried by photons, which are massless bosons. This force acts between charged particles and is responsible for many everyday phenomena, from the light we see to the way magnets stick to your fridge. In the Standard Model, electromagnetism is unified with the weak force under the electroweak theory. Strong force is what holds the nuclei of atoms together. It's the most powerful force in the Standard Model, carried by particles called gluons. Without the strong force, protons and neutrons wouldn't stick together and atoms as we know them wouldn't exist. This force operates at incredibly short distances, but its effects are vital for the stability of matter. Weak force is responsible for processes like radioactive decay. It's carried by the W and Z bosons, which are much heavier than other force carriers. The weak force plays a crucial role in the sun's energy production and in the transformation of particles. Although it's weaker than the strong force and electromagnetism, it's essential for the universe's evolution. Interestingly, gravity is not included in the Standard Model. While it's one of the 4 fundamental forces, gravity is described by Einstein's theory of general relativity, not by quantum mechanics. Physicists are still searching for a way to unify gravity with the other forces, which would lead to a more complete understanding of the universe. Higgs boson is a special particle in the Standard Model. It's associated with the Higgs field, which gives mass to other particles. The discovery of the Higgs boson in 2012 at CERN was a major milestone in physics, confirming a key part of the Standard Model. Without the Higgs, particles would have no mass and the universe would be unrecognizable. Symmetry plays a crucial role in the Standard Model. In physics, symmetry refers to the idea that certain properties remain unchanged under specific transformations. The Standard Model is built on mathematical symmetries that dictate how particles and forces behave. These symmetries help explain why the laws of physics are the same everywhere in the universe. For every particle in the Standard Model, there's a corresponding antiparticle. Antiparticles have the same mass as their counterparts but opposite charges. When a particle meets its antiparticle, they annihilate each other, releasing energy. This concept is vital for understanding phenomena like antimatter and has practical applications in technologies such as PET scans and medicine. Quarks possess a property called color charge, which is unrelated to actual color. This property is essential for the strong force, as it determines how quarks interact via gluons. Only combinations of quarks that result in a color-neutral particle can exist freely, explaining why we never see isolated quarks in nature. Standard Model organizes fermions into 3 generations. Each generation contains 2 quarks and 2 leptons with increasing mass. The first generation includes the up and down quarks electron and electron neutrino. These make up most of the visible matter in the universe. The second and third generations are heavier and less stable, appearing mainly in high-energy environments. Neutrinos are among the most elusive particles in the Standard Model. They have extremely small masses and rarely interact with other matter, making them difficult to detect. Despite this, neutrinos are incredibly abundant, streaming through the universe and even passing through your body right now. Studying neutrinos helps scientists probe the limits of the Standard Model. The Standard Model is based on quantum field theory, which treats particles as excitations in underlying fields. Each type of particle has its own field, and interactions occur when these fields interact. This framework allows physicists to make incredibly precise predictions about particle behavior and interactions. Experiments are essential for testing the predictions of the Standard Model. Particle accelerators like the Large Hadron Collider at CERN smash particles together at high energies to reveal new particles and interactions. These experiments have confirmed many aspects of the Standard Model and continue to search for new physics beyond it. While the Standard Model is incredibly successful, it has limitations. It doesn't explain gravity, dark matter, or dark energy. These mysteries suggest that there's more to discover about the universe. Physicists are constantly searching for new theories and experiments that can fill in these gaps and provide a more complete picture. Many physicists are working on theories that go beyond the Standard Model. These include supersymmetry, string theory, and theories involving extra dimensions. While these ideas are still being tested, they offer exciting possibilities for understanding the universe at an even deeper level. Dark matter and dark energy are two of the biggest mysteries in modern physics. The Standard Model doesn't account for them, yet they make up most of the universe's mass and energy. Scientists are searching for new particles or forces that could explain these phenomena, which could revolutionize our understanding of the cosmos. One of the great puzzles in physics is why the universe is made mostly of matter, not antimatter. The Standard Model predicts that matter and antimatter should have been created in equal amounts during the Big Bang, but something tipped the balance. Understanding this asymmetry is a major focus of current research. Physicists are always on the lookout for new particles that could expand the Standard Model. Discoveries like the Higgs boson show that there's still much to learn. Advanced detectors and accelerators are pushing the boundaries of what we know, and every new particle found could unlock new secrets of the universe. A major goal in physics is to unify all the fundamental forces into a single theory. The Standard Model unifies electromagnetism and the weak force, but gravity remains separate. The search for a theory of everything continues, with the hope that one day all forces will be described by a single framework. Mathematics is the language of the Standard Model. Complex equations and symmetries describe how particles interact and how forces operate. These mathematical tools allow physicists to make precise predictions and design experiments that test the limits of our understanding. Particle accelerators are powerful machines that speed up particles and smash them together at high energies. These collisions can create new particles and reveal the fundamental structure of matter. Facilities like CERN's Large Hadron Collider are at the forefront of this research, helping to test and expand the Standard Model. To study the results of particle collisions, scientists use sophisticated detectors. These devices track the paths of particles and measure their properties. The data collected is analyzed to look for patterns and anomalies, providing insights into the fundamental laws of nature. Modern particle physics is a global effort. Scientists from around the world collaborate on experiments, share data, and develop new theories. This spirit of cooperation has led to many breakthroughs and continues to drive progress in understanding the universe. While the Standard Model might seem abstract, its discoveries have practical applications. Technologies like MRI scanners, PET scans, and even the internet have roots in particle physics research. The quest to understand the universe often leads to innovations that benefit society in unexpected ways. Educating the public about the Standard Model is vital for inspiring the next generation of scientists. Outreach programs, science museums, and educational videos help make complex ideas accessible and exciting. By sharing knowledge, we ensure that curiosity and discovery continue to thrive. Women have made significant contributions to particle physics and the development of the Standard Model. From pioneering researchers to leaders in major experiments, their work has shaped our understanding of the universe. Encouraging diversity in science leads to richer perspectives and more innovative discoveries. Many brilliant minds have contributed to the Standard Model. Scientists like Richard Feynman, Murray Gell-Mann, and Sheldon Glashow developed key theories and made groundbreaking discoveries. Their dedication and creativity continue to inspire physicists around the world. Computers play a vital role in particle physics. They process vast amounts of data from experiments, run complex simulations, and help visualize results. Advances in computing power have made it possible to tackle problems that were once unimaginable, accelerating progress in the field. Visualization tools help physicists make sense of complex data. Graphs, charts, and computer-generated images reveal patterns and relationships that might otherwise go unnoticed. These tools are essential for communicating discoveries and advancing our understanding of the Standard Model. The Standard Model isn't just about tiny particles, it also has implications for the cosmos. Understanding particle interactions helps explain the evolution of the universe, the formation of elements, and the behavior of cosmic phenomena. Particle physics and cosmology are deeply connected fields. Despite its successes, the Standard Model leaves many questions unanswered. What is dark matter? Why do particles have the masses they do? Are there more fundamental particles yet to be discovered? These open questions drive ongoing research and keep the field vibrant and exciting. The future of particle physics is full of promise. New experiments, more powerful accelerators, and innovative theories are on the horizon. As technology advances, our ability to probe the universe's deepest secrets will only grow, leading to discoveries we can't yet imagine. Public interest in particle physics has grown thanks to discoveries like the Higgs boson and the excitement of large-scale experiments. Science festivals, documentaries, and online resources make it easier than ever for people to engage with the wonders of the universe. The Standard Model has transformed our understanding of the universe. It's a testament to human curiosity and the power of scientific collaboration. As we continue to explore the unknown, the legacy of the Standard Model will guide and inspire future generations of scientists. Physics reveals the beauty and order underlying the universe. The Standard Model, with its elegant structure and predictive power, is a shining example of this beauty. Exploring the fundamental laws of nature not only satisfies our curiosity but also connects us to the cosmos in profound ways. The discoveries of the Standard Model inspire young people to pursue careers in science and technology. By fostering curiosity and encouraging exploration, we ensure that the quest for knowledge continues. The future of physics depends on the passion and creativity of the next generation. Asking questions is at the heart of science. The Standard Model began with simple questions about the nature of matter and grew into a comprehensive theory. Every new discovery starts with curiosity, and the willingness to ask why drives progress in physics and beyond. The creation of the Standard Model is a remarkable achievement in human history. It represents the collective effort of thousands of scientists over many decades. By celebrating these achievements, we honor the spirit of discovery and the endless possibilities of science. As we look to the future, the Standard Model remains a foundation for new discoveries. The journey to understand the universe is far from over. With each experiment and new idea, we move closer to unlocking the deepest mysteries of existence. Thank you for joining us on this exploration of the Standard Model of particle physics.